supersymmetry with a twist. So this is with collaborators Nathaniel from Keong and David Finner. Nathaniel is at UCSB right now, I think. Okay, so before I go to the bulk, let's just go through a little bit of introductory background material. So as we all know, we have Large Hadron Collider in particle physics. So far, we've discovered the Higgs boson, and we've confirmed many standard model predictions. So this is taken from CMS. There's a lot of different standard model processes, and all the experiments so far have more or less is consistent with the predictions. Although there are few tantalizing hints of new physics, which I won't be talking about today, I think it's fair to say that standard model is a success. And right now the LHC is pushing the energy frontier at 13 TeV, and we'll continuously test standard model at high energies. And on top of that, we also have a mind-blowing movie, according to the New York Times. So, Particle Fever, I'm sure most of you have probably seen it. So I think it's fair to say that it's a good time to be thinking about particle physics right now. Okay, so despite all the success, there's still some strong theoretical problems or issues that we have. And so one of the most well-known problems is the hierarchy problem. So the question is, why is the electroweak scale so much lower than the Planck scale? And so why is the electroweak scale, which is 100 GeV or so much smaller, despite the fact that there could be potentially quantum corrections and so forth? So we could solve this through a variety of models. It could, maybe the Higgs is related to some other particle through some symmetries, which will forbid these corrections through composite or little Higgs models, maybe extra dimension or supersymmetry or a combination of these. And also another direction is that maybe it's just anthropics. There could be cosmological solutions that's sort of gaining popularity recently. And I guess, and to a certain extent, all this can be summarized by sort of this artist's interpretation of the hierarchy problem by this artist. It's sort of like, I would say, a mess, right? There's a bunch of, I don't know how you would interpret this, but there are many different directions. Some of them could lead to beautiful structures and whatnot, but it's anyone's guess at this moment, right? Okay, so back at the LHC again, right? So usually, many of these solutions to the hierarchy problem will postulate new physics around TeV or so. Unfortunately, so far, as I've said before, at the LHC we've confirmed most of the standard model predictions, and we haven't seen new particles yet. And this atlas plot, or sort of roughly summarizes the status of all the new particle searches. This is updated with the 13 TeV data. And these are f-SUSY searches, but it's useful for other generic new physics models as well. And generally, there's many different variety of searches, and the bounds are roughly of the order TeV or so, right? So if you try to solve the naturalness problem, you predict new particles, but then you have to reconcile with the fact that we haven't seen them. Then, sort of from the bottom perspective, really solving this hierarchy problem is to come up with models that sort of accommodate both LHC constraints and the naturalness requirement. And also note that most of these searches, the most stringent ones, for example, there's some, I guess it's hard to read here, these long-lived particles, and there are a bunch of Guino searches and scorch searches, and some of the most constraining searches actually come from color particles. Because LHC as a hadron collider, the largest processes is to produce new colored state. So it's really, the LHC is really sort of like a QCD collider, if you wish. So then, from the bottom-up perspective, then you can ask, what exactly is causing the hierarchy problem? And to the leading order, and at one loop, the most dominant contribution to the Higgs potential, leading correction, comes from the top loop, right? And then basically, in order to reduce so this top loop has a large sensitivity on the UV scale. So in order to remove it, we need some new contribution that's sort of related by symmetry to this process, and that sort of cancels out the sensitivity to UV physics now. So from the bottom perspective, we really need some new loop contribution that cancels this one. But then you can ask the question, what's sort of the minimum requirement for that to happen? So the structure of this diagram is that there's this Yukawa coupling, and then also the fact that there are 3 tops. And this is really basically it. So you can cancel it through squarks, for example, or through some top partners. But really what's important is that this coupling is related to this coupling here, and the multiplicity are the same. Right? So the requirement is related coupling, and the multiplicity is related. Then but then we see that because we only need the times 3 multiplicity, it's not necessarily the case that the top partners need to be color charged, right? If somehow we can impose the right multiplicity and the same coupling, that will be enough to remove this quadratic divergences or the sensitivity to UV, right? So then, sort of, many of the naturalness model can be summarized in this little table, although there are additional possibilities, but at least the ones with top partners can be summarized here. So, for example, in the traditional model, you have supersymmetry, where your Yukawa is related to a quartic through f-SUSY. Then your top partner is colored, right? Then you'll be bound by Higgs constraints. You can also go to little Higgs model, composite Higgs models, where your top partner is a fermion, right? But then in this case, they're also colored. But then what could happen is, on top of these global symmetries, you can impose additional discrete symmetries. For example, you could have multiple copies of standard model, right? And then and usually they're called the mirror sector or the folded sector. And then in this sector, you can also then the coupling, the Higgs coupling to different copies of standard model could be the same imposed by discrete symmetries. Then you can arrange the spectrum in such a way that perhaps the top partners will be living in these mirror worlds in such a way that they don't need to be colored, and then in such a way that you can evade LHC constraint. So for the f-SUSY case, you have f-SUSY plus a discrete cross a discrete symmetries in such a way that your top partner is really a stop living in a different sector with a different color charge. Or in the composite case, you can have twin Higgs models, and these mechanisms were originally proposed by these 2 papers. But today, I mostly focus on the folded supersymmetry case. Okay. Now let's sort of go over exactly how that works, right? So first, we have supersymmetry. So imagine you supersymmetrize standard model, then you have the top, and there's a stop, right? So the Higgs coupled with these 2, right? So if I just have this sector, then the UV sensitivity, the quadratic divergence is canceled between these 2 guys. Then on top of that, I can add a Z2 called the folded symmetry. You can duplicate the MSSN sector. And then you can also arrange it such that the color, the SU3 color gauge group, is also charged under the C2. So there's an extra SU3 folded color, if you like, right? Now, in order to have the folded mechanism, we would like to have a heavy stop in the standard model, in the MSSN sector, and a light stop, or folded stop, or for stop, if you like. Then you start having funny names. Anyhow, okay, so you have light top and light stop in such a way that the quadratic divergence would cancel. However, you notice some problems now, right? So if I lift this for top, then it's a massive fermion, And given that it's a massive fermion, it has to be Dirac. So the lines here denotes one complex degree of freedom, right? So in some sense, I need an extra, sort of an extra wild fermion. And by supersymmetry, then my f-stop also need more. I need more f-stops, right? But then you ask, whoa, there's a Z2 here, right? Then what happened to this Z2, right? You could say the Z2 is approximate, not exact, but let me not go to that route. Let me say that there is a Z2 symmetry. Then I have two vial fermions and one fermion. I have to reconcile with the fact that there's only one. So then to fix it, I have to add another one. But then it has to be heavier because in the standard model we only have one light top. But I have to add another one here, and I also have to sort of add a stop here. But then I come in the same problem again. This is a massive fermion. I need an extra top quark to make a Dirac mass. So this keeps going back and forth. And then inevitably, you have a structure that says, hey, I sort of need an infinite tower of these guys in order for the mechanism to work. So we're led to the conclusion that if you want to impose this type of model, you're forced to consider extra dimensions. So you need to have powers of states that sort of cancels out the divergences step by step, right? This with this guy, and then jump back. Okay, so far so good? Questions? Okay, now, so we're sort of forced into this space where we have to consider supersymmetry in extra dimensions. So the minimal case is 5D, right? So with 5D dynamics comes with a bunch of extra baggage now, right? So in 5D, your f-SUSY generators comes in Dirac fermionic pairs instead of wild fermion. So you have extra supersymmetries from the perspective of the 4D physics. So in terms of 4D, your n equals 1 supersymmetry in 5D is really n equals 2 supersymmetry, right? So you sort of have to break f-SUSY twice. And to do that, there's a natural mechanism to do that. It's the orbifold and compactification with short mechanism, which I'll describe later on. So because I'm not sure if everyone's familiar with this. And in 5D, sort of all the multiplets comes with extra stuff. So for example, your gauge vector multiplet comes with it a chiral adjoint scalar. So you have two gauge nodes instead of one, and you also have an extra adjoint, which is sort of the fifth direction of the gauge field. And the matter also has to come from hypermultiplet. You have, so for example, the top quark superfield has to come with the top conjugate superfield. Okay, and then theoretically there are also some issues, right? Now you're doing 5D physics now, your theory is really non-renormalizable. So you're bound to have a low cutoff. But then on the flip side of that, because it's non-renormalizable, it means that all your UV contributions, when you do loop calculations, they're all going to be finite because of this extra f-SUSY too. And to a certain extent, your calculation will become UV insensitive, and to a certain extent, it gives you a predictive framework to calculate these f-SUSY breaking contributions. And other nice features that perhaps some people might not appreciate is that when you have 5D physics, you have a bunch of KK towers, and that means you have a bunch of tops with large Yukawa couplings to the Higgs, and that could help to generate a large Higgs mass for the Higgs in the 4D case, right? Because you have a bunch more tops that has few f-SUSY breaking. So this could actually help. And then other nice feature is that if you have a lot of states living in the bulk, their masses is generally just the mass of the KK level, so 1 over R. So this could naturally accommodate a complex spectrum. So all your state will be around 1 over R, and then you could have relaxed constraints from the others. Okay, so here is sort of the overview. I'll go into a little more details on the mechanisms in the black book because the equation is a little heavy, so I'm going to continue the blackboard for now. And there's a lot of references that I'll use in the discussion. Of course, there's the original paper, Schwartz, and then there are a lot of people who have worked on these 5D calculations with f-SUSY, Delgado, Lingerstorff, Kiros, and then there are also a lot of people working on the model building side, like Lorenz Hall, Barbieri, and whatnot. So, which I won't include on the talk. But anyway, let me continue on the blackboard. So I'll move over here. First of all, let me talk about, so for some of you this might be review material, but it's important to sort of know how we compute things with 5D models. So first, let me talk about how we break all the f-SUSY and get a 4D model, right? So start with a 5-dimensional model. You can imagine you have the Minkowski space across the extra dimension. But we know that we haven't seen a continuum of new particles yet, so this needs to be compact or small enough. So how do we compactify a line? So what you can do is you can go through what operations I can perform on R. There are two. So there's the operation of parity. You can send all the, imagine y is in R, you can send y to negative y. And there's also the translation operator that sends y to y plus 2 pi r. This sets the scale of the extra dimension. So if I modulo out these operations in some ways, then I'll get a compact extra dimension. So usually what people do is, you know that z squared equals 1, right? Because you flip twice, you get the same thing, and you can also construct this operator, what people call z prime, which is defined as z, right? And you see that z, you can just do a calculation, z prime squared also has to be 1. And this can be understood sort of geometrically. Imagine you have a line and pi r. You see that z sort of reflects, the action of z is reflection across this axis, and the action of z prime is reflection across this axis. It's a little complicated. You can try to track it. You can see a point here will get translated to here. I think it's, let's see. A point here will get flipped to here and will get translated to here. So, right, a point here will get flipped to here and it will translate to here. So it's basically flipping across. So we can see that, right? So, in a lot of model building, people usually consider the most simple case when z and z prime commute, right? Then all your fields can be categorized by their eigenvalues, right? So you demand that my field, you act on my field, is equals to, then it has to be plus or minus this way, right? And the same thing with z prime. Then you can get this table. If you write down all the fields that transform this way, you write down z and z prime. Your eigenvalues are either plus or minus 1, right? And then the kinds of wave function that satisfy this condition, you can solve the equation of motion in the 5 dimension, and you get something like this. Okay, so geometrically, this picture it should be clear because this function really is telling you that between the interval 0 to pi r, this guy is even across both boundaries. Right? So this is this wave function, and this wave function is just it vanishes on the boundary. You have a different boundary condition, and these guys are basically something like this, sort of a mixed boundary condition here. Right, and you see that if you look at the eigenvalues, the n's here have to be integer, and the masses for these guys are the masses roughly goes like n over r here, and this is n plus half over r. Mass goes like n plus a half over r. The mass here goes like also n over r. But n cannot be 0 here, otherwise the wave function is 0. Right? So this kind of spectrum basically will only leave you with only one 0 mode. So this guy is light, everybody else is heavy. At least the lightest guy in all of these are heavy. Right? So what you can do with this kind of models is that you can the most trivial thing you can do is you can just embed the MSSM in this framework, right? So in the MSSM, you want to have light gauge boson, right? And you want to have light quarks, right? If they live in the bulk, that is, which is what we're trying to do in the f-SUSY case, then everything else will have to live in these regimes, right? So usually the way people arrange things is that you have your normal gauginos here, and with the squarks, and you have two gauginos with the other squarks, and this is sort of the adjoint scalar that comes along with the gauge boson. And there's the conjugate quarks. Right? So to visualize this, you can see it in this spectrum. So mass and versus fields. Right? So the gauge boson has a 0 mode. Gauge boson has masses 1 over r, right? So these are gauge bosons. And then there's it's convenient to move some of these fields to the negative axis, keeping in mind that the mass is positive. And I'll explain why later. This is a useful way to see how the spectrum moves. So you can organize it in such a way that this scalar lives in the negative axis, right? And similarly for the quarks, this is the quark, which you see, and then the gaugino sort of lives somewhere in the middle. One.
So here you're imagining that n equals 2 is broken down directly to n equals 0. There's no approximate regime where you have n equals 1 supersymmetry.
In this setup, this setup is completely broken. Yes.
There's no intermediate n equals 1 regime. It's just broken sort of in one step and n equals 2 down to n supersymmetry.
Right, although yeah, I'll say that this is the simplest setup, but there's actually a parameter you can dial that you could achieve that, which is what I'm going to go to next. But this is sort of a nice way to visualize it for now, right? Now, so this is the simplest case right now, but in fact, in general, these two operators don't have to commute, right? I could have a much more non-trivial conditions, and let's see what happens. So what you can do is this translation operator, right? Initially, I have it sent to a phi plus 2 by r equals just plus or minus, right? That's what I initially have. But in fact, you can sort of make it more general. It could be some matrix here. And in order to break SUSY, you could set this matrix to not commute with SUSY, right? But then one possibility is just to have the SU2R symmetry, right? So you can have something like 2 pi, 2 pi alpha sigma 2. So when alpha equals a half, this is just -1. You can sort of exponentiate it out. So this way, you see that only fields that are charged under the SU2R will feel the non-trivial boundary condition imposed by this translation operator, right? So what happens is, so in terms of this table, corresponding to these fields, the ones that are charged under the SU2R are these fields, are the gauginos and the squarks, right? So what happened if I impose this condition is, then the solution for these guys will change. So this sort of becomes, I just change the half to alpha. You can check that this solution does work. Although it really is this is sort of a rough solution. Really, it's the solution is it's a doublet of SU2R. So these two, so the solution is more like sine, cosine. But schematically, really these two guys mix, and the mass spectrum changes, where you can sort of think of this instead of being a half R, it's alpha over R. So the picture is this: when you modify alpha from a half, you're basically shifting this guy up and down, right? So when alpha equals 0, then I'm not imposing a non-trivial boundary condition this way. Then the whole thing moves down. Then you have supersymmetry again. You have n equals 1 supersymmetry, right? So this you can dial, right? So if you dial. So when you dial alpha to 0, this is sort of the SUSY limit in MSSM. Right? Okay. Okay, so let's summarize a little bit. In the MSSM, now let's just look at the quark sector for now, for simplicity. But for the gauge bosons, the spectrum is basically similar. So for the quarks, you have the masses. The masses of these guys are n over r. So you have a massless mode here. And for the quarks, you have n plus alpha over r. Right? So in the MSSM limit, your SUSY breaking soft masses, for example, your gaugino mass, M1 or M2, whatever, is roughly going to go like alpha over R, right? And also your squark masses is also going to go like alpha squared R squared, right? Okay, so now let's go back to see, so how exactly would that work in folded supersymmetry, right? So imagine I have folded supersymmetry. I have a folded SUSY sector, and here comes the folded quark field, quark, and the spark. Okay. Now, if I just relate them by Z2, right? Just copy the spectrum. I don't gain a lot so far, right? I'm just sort of repeating the MSSM, doesn't really help me. Right? And also, I want to clarify that the Higgs lives in the middle. It does not charge under Z2. Right? Okay? So this is not very good. So I need some way to break this degeneracy here. I need to change the spectrum here compared to here. Okay, so what happens is, basically I need to break this Z2 in tantrum with breaking f-SUSY. Right? So what happens is I have to change this, the operation of the translation. Right? And what I can do is, instead of being just this SU2R, I can add in some dependence depending on whether you're MSSM or folded at MSSM. And there's sort of no continuous choice. What I can do is I can have a plus or minus sign in addition to this. Right? So when that happens, well, we've seen that when alpha equals a half, it's sort of equivalent to a negative sign. Right? So when I add in an extra plus or minus sign, let me just put this here. Right? This is equals to 1 for the folded sector. When I add in the plus or minus sign, it's sort of like adding a half to all your spectrum. And note that this sign does not break f-SUSY, so they all have to get a half for the fermion. All right, so.
I'm sorry. What did you do to get this half?
Right. So basically, we want to break this degeneracy. So right now, the masses here is the same as the masses on the folded side, right? But I really want the folded side to have light squarks instead of heavy squarks. Right? So I want the spectrum here to be different from here. What I can do is I can change the translation operator to incorporate the Z2 breaking. So this matrix has to involve the Z2 non-trivially in some ways. But then it's a Z2, so I don't really have much freedom. So what I can do is just add the Z2 sign, or a -1. But then a -1 is the same thing as alpha equals a half, right? So that means I'm just adding a half here. Right? Okay, now, so let me recall, in the MSSM, alpha goes to 0 is the f-SUSY limit. But in the folded MSS, I guess the folded f-SUSY, you want the exact folded f-SUSY limit is when you have light quark and light squarks, right? So basically this guy needs to be light, or alpha plus a half goes to 0, right? So for convenience, it's actually more convenient to talk about n minus a half. This doesn't really matter because I can always shift the index n to n plus 1. Right? So n plus a half is the same thing as n plus a 1 minus a half. So then then this limit becomes alpha minus half goes to 0. This is sort of the f-SUSY limit. And naively, this seems like, oh, it's okay, but there's actually, this comes with it quite a bit of a problem. So, because you see that even when alpha is exactly a half, I don't have f-SUSY. The f-SUSY is just broken in this case, right? The quark. To a certain extent, I don't have any symmetry, any special symmetry when alpha is equals to a half. So there's no reason to suspect that this is small in any way. As opposed to the MSSM side, I can say that, hey, the f-SUSY breaking masses are small. Now naturally small, so this can be small, and 1 over r can be large. But here, I'm sort of stuck where alpha minus a half doesn't really need to be small, but for the f-SUSY to work, it should be reasonably small. Although, in fact, there's a more dire problem. Right. So if you calculate the Higgs potential, say, hey, given this spectrum, how does it break electric symmetry, right? So in SUSY, the Higgs instability is driven by the top sector, right? So roughly speaking, your HR ball, the soft mass roughly goes like, there's a contribution from the top sector, top to tower, and in this case, 1 over r squared, because we're in extra dimension. So there's some coefficient here. So this will give you some instability. However, the gauge contribution will give you a positive contribution to the Higgs mass. So there's some contribution from the gauge sector. That goes like this, right? Now, in the alpha goes to 0 limit, these both go to 0. So you can actually say that the Higgs soft mass is small compared to the compactification scale. However, in this case, when alpha goes to 1/2, right, this will be 0 because of the folded protection. Basically, this guy cancels with this guy. So effectively, at 1 loop, this is 0. But the gauge contribution is not 0, right? So in the limit that alpha is equals to 1/2, because I'm not folding the gauge sector per se, because the gauge sector stays. There's no cancellation among different gauge fields, right? So in the exact folded SUSY limit, I have a positive contribution to Higgs mass, so I can't break electricity. I can't break the electroweak vacuum. So, and then this becomes a slight problem. So, and that basically tells you that alpha minus 1/2 cannot be so close to 0. It has to be a bit away. So that numerically, you can see that this roughly requires that this is larger than like 0.1 or so. Or basically means that alpha has to be a bit less than like 0.4. It can't be too close to 1/2 for electricity to break in half.
So your H field lives in the bulk in your 5-dimensional?
It could go either way. It could be in the Brane or the bulk, but mostly I'm talking about the quark sector and the gauge sector. That has to live in the bulk.
The reason I'm asking is, it seems like you haven't really, the only thing you've lost is radiative electricity, right? I mean, you can have a soft mass, an arbitrary soft mass where it makes up squared.
Yes, that's true.
Electrosymmetry.
Right. Okay, yeah, that's true. Although a caveat is that we are sort of restricting ourselves to a very specific SUSY breaking scenario with the search-walk mechanism. You could, of course, impose additional sources of SUSY breaking on the Brane, for example. You can just throw in an extra soft mass for the Higgs and whatnot, right?
I think even with Schwartz, if you had the right kind of Brane coupling, you could do an arbitrary soft mass. I mean, because one way you can think about Schwartz is doing Brane localized SUSY breaking. And if you allow sufficiently general couplings of H, I think you could probably get a soft mass for H thing.
Right, that is true. I mean, yeah, you could just throw in a negative. I mean, even in the kilo potential, you can just say it's negative or not. But to a certain extent, that becomes less calculable. So I guess for us, we define our model in the sense that right. I mean, you can of course do the most general analysis, throw in the soft masses and whatnot. But I guess for us, we're sort of trying to provide a little more, slightly more UV completion and with a specific SUSY breaking scenario, right? If you introduce a soft mass, then you have to ask, where's those SUSY breaking coming from? Of course, you can have engagement with Brane and whatnot, but we try to avoid it. But I agree, yeah, that there's nothing stopping you from doing that, but it requires a little extra structure. I guess for us, we're sort of approaching it from the naive point of view, like what's the most minimal setup that you can try to see if it works out. But of course, you can add more SUSY breaking, then you have more parametric freedom. The parameter space opens up, it's much larger, but also requires more non-trivial structure, which we didn't study for us. And so this is sort of the most minimum setup. At least with this most minimum setup, this is this is the constraint, but I agree that it could be changed to a certain extent. Right? Okay, so given this setup, let me see if
So you're saying for these values of alpha, you should get radiative symmetry breaking?
yes, you could. Yes, you could get to one. Okay. Yeah. So I guess roughly speaking, yeah. So with these kinds of constraints, you could get an instability large enough that you can trigger electroweak symmetry breaking. And I think I'll skip the rest of the technical details and show you some results. So is there any question of the general setup, at least the basic idea of the issues with f-SUSY and how it works? Okay. Okay, so basically we've seen how f-SUSY works. So if LHC is a high stake poker game and you have all the constraints and stakes on the ground, let's see how folding will work for you in practice and see if it works. Okay, so the first thing we try is put the Higgs in the Brane. So far I've told you that the matter and the gauge field sort of has to be in the ball, but there's a freedom on where you put the Higgs, right? And so you could just put Higgs on the Brane. So schematically, you have an interval, Higgs lives here, and the Yukawa coupling also lives here. The Higgs couples the bulk fields to right here. And then you have SUSY breaking in the bulk, and that will feed back to the Higgs sector to gauge coupling on the Yukawas. And then we went through a one-loop calculation, get the potential. It turns out that the B mu term generated is too small for this setup, right? Of course, you can add in by hand extra B mu term, but we took a different approach. We just sort of we say, hey, we define our model by saying that there's no extra sources of SUSY breaking. So we generate a larger B mu term, or effective B mu term, by adding a BMSSM potential on the Brane. So this roughly parametrizes what happens if you add extra Higgs sector. So if you add a singlet here, at low energy, it roughly generates, to leading order, generates some higher dimensional operator here. So this is just taken as the convenient parameterization.
Is there a symmetry that forbids a B mu term on the Brane?
Not exactly. But at least for our setup, given the source of SUSY breaking, the B mu term we come to is just too small. To a certain extent, the cancellation is...
No, I know, but you said you didn't put it in because it was minimal, but it's not obvious to me that there's any symmetry that forbids it.
Yes, but I'm not sure what it will couple to. I mean, it could certainly couple to... Well, if you take the picture that short mechanism is the radion mediation, you can certainly add some non-minimal coupling to the radion, but that's dictated by gravitational interaction. So I guess you could impose some non-minimum setup, and indeed, if you can generate a larger B mu term, it would make this model a little more appealing. But I'll show you that. I'll show you in the next slide what the parameter space looks like. So at least this is viable right now. So here are the results. So given a mu term and this 1 over m, then you can do a parameter scan and see where you get the right Higgs mass and whatnot. So it's not so difficult to get the right Higgs mass. In fact, a lot of the times your Higgs mass is actually too heavy, but you can still get it. But unfortunately, in this model, the dominant constraint comes from this pink curve comes from global fits to your Higgs doublet model. I think we used Higgs fitter. What exactly we use? This is mostly coming from Higgs mixing, from the global coupling fits, and there's a large chunk of parameter space that's been excluded, and you end up getting pushed to a region where your tuning is rather large. So the tuning here, we just compute the derivative of log of the depth of the potential. And so roughly, the variable parameter space, you have roughly order 1 in 1,000 tuning. So this is at alpha equals a third. You can change alpha a little bit, and this will shift around a little bit, right? And this region is where mu over m is larger than a half. This is where the BMSS term approximation will break down. Then you really have to include the singlet and whatnot and compute the full thing. But we can, and then the parameter space will become much bigger, so we didn't bother doing that here. But at least you have some region here where you have variable 125 GeV. 1 over r is quite large because tuning is large. You see that 1 over r is 30 TeV. But it's variable, but it's still tuned. And also the message is that your dominant constraint comes from Higgs mixing because you have to change the Higgs sector to accommodate like symmetry-breaking. So that's still the dominant constraint, and it's not dictated by folded supersymmetry dynamics. Just not. Sorry? Yeah, and also this figure shows you the contours of other stuff. Like tan beta is fairly big, and we checked that the Higgs to tau heavy Higgs searches is subdominant to this, and then also contours of the pseudoscalars also around TeV or so.
Can you remind me what capital M is?
Yeah, capital M is just sort of the size of this extra coupling on the Brane. Right? We just parameterize it as one of them. So larger M means smaller. Right.
Okay.
Yeah.
And do you understand why does mu have to come out to be so large? Why is mu coming out so big?
Right, so basically you have to, let's see.
That's obviously, seems like that must be somehow, well, is either, I mean, I'm wondering if there's some source of fine-tuning and a large mu is what you're using to cancel it.
Yes.
Or if somehow there's a phenomenological reason that mu is large and therefore you have to tune something else. I'm just trying to, mu is obviously very closely tied to your fine-tuning, so
yes.
I'm wondering, what is it that's making mu large?
Yeah, it's mostly experimental constraint. In fact, this contour keeps going to the left, like all the way to like, say, 200 GeV or so, but it's just that it's all ruled out by Higgs measurements.
So all the Higgses are
yeah. So yeah, this is like really big, but I just don't. The tuning here is mild, but it's ruled out. So exactly. So more work needs to go into the Higgs sector to fix it. And let me just say that if you put in like just by hand a B mu term on the boundary, right? You could alleviate the tuning quite a bit. You can lift much further here because all the pseudoscalar can be pushed heavier, and then you can, I think maybe like 1 in 100 or so tuning you can live with. But
I mean, just my perspective. I mean, I understand that if you just somehow have pure Schwartz and you just say that God broke supersymmetry, there's no dynamical f-SUSY-breaking or something, then yeah, maybe you could say you can't write down a BU term without breaking some additional symmetry. But if you instead just have, there is some breaking of SUSY and it's getting communicated to the radion, and that's how the bulk fields are feeling it. It's very natural in that context to have these Brane localized terms. And it seems like you're hurting yourself a lot.
Right, to a certain extent, that's true.
And this doesn't really intrinsically have to do with the folded SUSY thing, idea that you're trying to exemplify. So,
right. Yeah. Right. Yeah. I agree. So, although if you include a B mu term, naturally you would also include other soft masses in the scalar potential, and they'll be of the same order. And then your parameter space is sort of, I guess it's not as predictive. You just have a bunch of soft masses, B mu term that you can dial, and then you can get a particular breaking scenario. That's certainly
those are different things. It's like you can have the MSSM.
Yes.
The MSSM is a very good solution to the hierarchy problem, but it's not very predictive.
Yes, I
so
agree.
then, in addition, you may be interested in particular assumptions about SUSY breaking, but I think here you would like to show that you have a good hierarchy problem before you start making predictive. You've got a good solution to the hierarchy problem, which means you don't have large fine-tuning before you start going into predictive modules, I would think.
Right, yeah. Although I would say that there have been quite a bit of work going into just general phenomenology of these neutral natural models, and for them, yes, you could just parameterize it and assume that there's some light stop somewhere. I guess for us, we were trying to say, hey, what's some reasonable UV, like semi, I mean, this is not really UV completion, but sort of like semi-UV completion that is plausible.
And also, I'm sorry, because I just maybe you said it, but so what is the new ingredient in this work compared to previous works on folded SUSY?
Right. Well, basically, in previous folded SUSY, they just assume that the most naive search short will give you the right electrosymmetry-breaking and whatnot, but that's not the case.
So
right?
Your difference is you did a more careful job of
and basically show that it's not as trivial to get electrosymmetry-breaking. But in the MSSM case, you can actually get it to work even this restricted model. You naturally get electrosymmetry-breaking. You can even get the right 125 GeV mass just in this really. If you just have mu and alpha, and you could get it to work. It's somewhat fine-tuned, but it works out of the box. But and for the SUSY, you need a little bit more. I guess sort of the takeaway message is, at least in this scenario, there's too much cancellation between from the folded sector. It's a little too efficient to a certain extent, and it sort of kills a lot of your soft terms, right? At least numerically when you compute it out. But anyway, this is not the only model. We go to the other model. So Higgs on the brane didn't work. The next thing we try is to put Higgs in the bulk. It's sort of a natural thing to try. However, we immediately see a big issue because in the bulk we have this SUSY breaking thing. We have this search short SUSY breaking. So everybody in the bulk gets a large SUSY breaking masses except the folded guys. But then the Higgs is not folded. It's neutral on the Z2. So immediately you get a large soft mass proportion to alpha over n, which will stabilize the Higgs VEF immediately. It doesn't break electrosymmetry. And also, of course, you also get light xenos because the quarks are light, xenos are light. So that's not good. So one way to solve it is just to have a more complicated search short condition. Basically, you can introduce two Higgses. So instead of just having the periodic boundary condition, instead of just basing it on SU2R, you can base it on sort of a combination of SU2R symmetry and the Higgs SU2 Higgs symmetry from the two bulk Higgses, right? So if you try that, then you see that one linear combination of these HA and HB will be 0, and they will be light, right? And then Higgs-xenos will now be heavy now because of this short twist. And let me just go back to this diagram. And in the IR, you actually only have one Higgs because there's only one linear combination, exactly one linear combination that is flat, right? So how do you generate the Yukawas then? Well, what you can do is you can couple to the quarks here, on the up-type quarks here, and you can couple to the down-type quarks with the HB conjugate, which has, sort of anti-fundamental charge on the SU2. So you can couple the other types of Yukawa here. So you can actually generate a completely standard model, more or less standard model like sector in the IR. Although this comes with a unfortunate issue is that if you do this, you have no gauge coordinate, right? So now my HA plus HB conjugate dagger is my Higgs, right? But then the gauge coordinate goes like HA minus HB, then HBC, then this goes to 0. So I have no coordinate. It's living in a flat direction. So in order to save it, you can add a singlet on the brane, sort of the NMSSM scenario, and then you can get it to work. So So now you have one Higgs in the IR in addition to a singlet. And here's some slices of the parameter space. So you have three, in this theory, you have three parameters. There's the alpha, there's the lambda, and also ms. Although the dependence on ms is not very strong. So let me walk you through the plot. So here I fix ms to 0.4 in dimensions of 1 over r, and scan over different alpha and lambda. You can see that alpha sort of has to be large-ish, somewhat close to a half, but not too close, to get electrosymmetry breaking. If alpha is too large, then you can't break electrosymmetry, right? And then you can get the right Higgs mass 125, this contour, right? And this brown contour is the tuning, so you can actually naturally get 1 in 10 tuning roughly in these regimes. Your 1 over r is a few TeV, and this red constraint actually comes from jet plus met, right? Because even though your 1 over r is 3 TeV, you still have some reasonably light MSSM squarks and gluinos, and this constraint remains the dominant one. Right. Although right now this is a TeV, so from Atlas it's a little higher now. I think just slightly by a few hundred GeV. So, but you can actually accommodate 1 in 10 tuning in this kind of model, and you can also take different slices. You can fix alpha to 0.3. So 0.3 roughly tells you that your folded stop is half as light as your stop. So your folded stop is 600 GeV, your normal stop will be 1.2 TeV, right? At least in this slice, right? The closer you get to a half, the heavier your stop will be compared to your folded stop, right? So in this parameter space, different slice, you can naturally get 125. You can have 1 in 10 tuning, but your lambda has to be fairly large, but it all works out.
Do you have some example spectrum, let's say 10% tuning or something you have? And do you know, or can you say, like, for example, what is in that white regime, when you have, say, 10% tuning, 125 GeV Higgs, what's the lightest colored, what's the mass of the lightest colored guy?
Right, yeah.
Like
yeah, we don't have a specific spectrum, although you can roughly read it off the plot, because everybody gets their SUSY breaking masses from Schwartz, so leading order, they all have the same mass, alpha over r. So for example, here, r is 3 TeV. For example, if you take this parameter point, I guess here, 3 TeV, then alpha times 3 TeV is like 1 TeV. So all your squarks and gluinos would be around a TeV or so. Although there's still some uncertainty here, because higher dimensional operators on the Brane or whatnot could change this by 10%, 20%. And this is sort of important. You would hope to get like an exactly compressed spectrum. That would be great. But you can evade a lot of the constraint. But if you put in some honest high dimensional operator, you expect some changes. Right?
In this scenario, the stop is the colored stop, is it the same mass roughly as the other squarks? There's no hierarchy between the stop and the other squarks?
Right, oh yeah, you do generate some extra masses from electrosymmetry breaking, yes. Although that's subdominant, although we didn't take that into account.
Yeah, so they're roughly the same. So
they're roughly the same.
TeV or so.
Right, but they're 3 TeV, yeah, there's some splitting. Okay, so I guess right on time. I guess with that I come to my conclusion. So hopefully I've convinced you that, I don't know to what extent, but mutual naturalness and SUSY could give you potentially quite attractive solutions to the hierarchy problem. And then we tried the most minimum implementation of this for the supersymmetry scenario. And we said it does not, naively, it does not break electric symmetry. But then we sort of take the next step, just slightly more than minimum extensions. And we show that you could achieve electrosymmetry breaking. In the Brane Higgs case, you could do it, but it's still somewhat fine-tuned. In the bulk Higgs case, I think we show that you can achieve quite a nice tuning. It's competitive to the other models, and it's also very predictive. But then, in all these models, and because of the discussion we have, the alpha cannot be too close to a half, you see that all the MSSM partners to the standard model, they're not so much heavier than the folded guys. So your dominant constraint will still be dictated by conventional searches. So I guess the takeaway message is, the punchline is, in case you've been asleep the whole talk, at least this message. So folded SUSY could work, but the caveat is that traditional strategy will still apply, so you still have to play the poker game of, you've got to hedge your bets and so thanks. So, questions?
Any questions?
Yeah, so if you can go back to the last plot you showed.
Yes.
So naively, I would imagine that here the constraints from the gluino, the standard gluino,
yes,
play an important role. Right? It's probably the driver of the...
Yeah. It is the gluino. It is the gluino.
Right. So is there any easy way that you can think to help solve the problem?
Really, the biggest problem is the gauge softmass. So you really have to fold the gauge sector in some ways to cancel it out, because the folded SUSY only folds the quark sector. But then, in order to do that, you sort of have then the Higgs is charged under SU2. Then, to a certain extent, the Higgs has to be charged under this bifold symmetry. Then you sort of inevitably led to the conclusion that you have to mirror the Higgs. Then you're kind of like doing twin Higgs now. So. Right, so it's possible, but we haven't gone into that direction. So really, it's like you could combine twin Higgs and folded SUSY. So it's possible, but we haven't exactly explored that direction.
Do you have to use Schwartz? I mean, could you? I mean, I'm not even sure if this makes sense. I'm just very really never thought about this stuff. But could you somehow have some twisted boundary conditions that by themselves preserve SUSY and then use some other SUSY breaking mechanism, like Brane localized SUSY breaking or something like that? I'm not even sure that makes sense.
Right, certainly you can do that, but let's see. But then,
I mean, could you get? What I'm asking is, could you get some? You can definitely do that, but could you get something like a folded spectrum from that?
You mean not going to extra dimension? I guess.
No, going to extra dimensions, but not using Schwartz.
Right, but
SUSY breaking mechanism.
Right, but at least the quarks, in order to have the freedom to dial the squark and the folded squark up and down, you sort of need this SUSY breaking in the bulk, right?
Yeah, maybe. That was sort of my question. I wasn't
right.
clear on that.
I mean, you could. You're saying if you could just add a Brane coupling and forget about.
I mean, somehow you have some non-trivial boundary conditions that say break n equals 2 down to n equals 1. So there's some non-trivial sort of twist there, but it preserves n equals 1 SUSY. And then you somehow have n equals 1 broken down to n equals 0 in a Brane.
Right, yeah. Although the difficulty is to correlate the SUSY breaking with the Z2 breaking, because at the moment you want to lift the squark, you also want to lighten up the folded squark. So this correlation would be kind of non-trivial if you just add in some soft masses. Like why is it that there's a negative soft mass that's sort of equal to the positive soft mass? Then I guess you have to explain that. So the boundary condition.
No, I have no reason to think it works. I'm just wondering if you guys thought about it.
Yeah. Although,
If anybody thought about it.
Yeah, one way you can sort of escape these issues is you can sort of do an effective folded SUSY model. So like. I know Simon and Berkeley work with Mass Dressler, they did something like that. So basically you can have a quiver that sort of mock up the 5D physics and have the Z2 to be not exact. So you can have one, basically when you go up the tower, when I go to the explanation with one, you got to have fermions here, then Z2 scalar here. At some point you could stop and say, hey, my Z2 is only as good as the bottom 3 guys or something. And say, hey, I just have an extra fermion here, whatever. And you can say, hey, how much does my naturalness depend on this fact? But then you still have to explain why there's an approximate Z2 because it's not an exact Z2, so it seems a little weird. But you could try that.
No other questions? Let's thank him again.